So we're going to continue looking at this idea of covalent compounds and what they can do. But now we're going to look at polyatomic ions. Now, a polyatomic ion is a group of two nonmetals like this, and they have a charge associated with them. So this is not the same thing as saying SO4, sulfur tetraoxide. This is the sulfate group. These are very commonly included in a lot of oxidation reduction reactions. And if it helps you, once you figure out SO42 minus's oxidation numbers, they're going to still be the same oxidation numbers in any compound that has SO42 minus. So what will throw people off is the idea that there's a charge. Up until this point, we've just been doing things that have neutral. Well, it just works the exact same way. It's just that it needs to add up to the charge. So we look at oxygen and sulfur. None of them are on the list, so we based it on electronegativity. Oxygen is more electronegative than sulfur, and so oxygen is going to be -2, and there are 8 of them. I'm sorry that there are 4 of them. I'm thinking ahead. So it needs a total of -8. Now, I know that my whole thing is going to add to that -2 charge. Before we were adding to 0, but because it's a polyatomic ion, it has a -2 charge. And we don't know sulfurs, so we'll just call that X. And then to figure it out, we'll say, and I'm going to move this over here, X minus 2, X minus 8 equals -2. We're going to add 8 to both sides so that we get X equals 6, positive 6. That's what sulfur is going to have to be. It's going to have to be a +6. So it's still the same idea as before, as the last video when you had these covalent things stuck together. It's just that now note that if the species has a charge, then that's got to be taken in consideration. So anytime you have SO42 minus, the S is always going to be a +6 and the O is always going to be a -2. Let's look at the PO4 example. So PO4, O is going to be -2. There are 4 of them, and so that's -8. I don't know my P, but I know the whole thing has to add up to -3. So I'm going to take this same picture, but this time it adds up to -3. I'm going to add 8 to both sides, and I'm going to have X equals +5, which is what phosphorus's oxidation number has to be. And again, if you get PO43 minus, those are the oxidation states that will always match with PO43 minus. So it's just good to know because they're really common. Finally, we're going to zoom in on one more little thing right here, this Na2SO4. So in this case, we have 3 elements. So we've just talked about one element having preference over the other. Well, if you've got 3, you give preference to 2 of them. So let's look at our little chart over here. So we definitely can give preference to the alkali earth metals. So we can say that's going to be +1, and there's 2 of them. So the total here is going to be +2. And then we can look at the SO and the 4. They aren't in the first 4 of the list, so it's based on electronegativity. The oxygen, it's going to get its charge because for the same reason we just talked about, it's going to be a -2, and there are 4 of them. And so that means I've got a -8, and the one I don't know is what's going to be sulfur. This whole compound is neutral as written. So what I have is 2 plus X -8 equals 0. So I'm going to go ahead and put the 2 with the 8 so that I have -6 equals 0. And then I'm going to say X equals 6. And notice that I can change this out and I can make it a 6. And then you can see I've got my value for each sodium there, my value for my sulfur, and then my value for my oxygen. And you'll notice, comparing up here, this SO42 minus had the +6 and the -2. This has a +6 and a -2. So that's how you'll do it when you have multiple elements in there. You just are going to have to figure out one of them. If you've got 3 elements, use preference for 2 of them, and then you've just got that last remaining one you can do the math for.